Okay, so there are three problems. I'm quickly going to explain them, draw their diagrams, and then you can tell me how to solve them. It's related to Coulomb's law. I'm sure you haven't studied that thing because that's pretty basic. So the first question, one, we have a square. So let me see if we can draw a square. And we have charges at its corner. We have a charge with magnitude plus 2q. We have a charge at this corner with magnitude q. Here a charge with magnitude q, and here a charge with magnitude q. So you are going to tell the direction of net force on this charge, which is at the bottom left of this square, due to all other three charges. Just the direction. We are not going to calculate the magnitude or numeric value for this one. Think about it, and I'm going to put the second problem here. So question 2 is we have a charge at this point, and this charge, let's call this one as Q1, have magnitude of 17 nanocoulomb. And then we have three more charges, and they lie, let's say, at this point, at this point, and at this point. You see they lie like on a semicircle. So the distance of these three charges is that's all same from this charge, and this distance is given, it's 5 centimeter. Since we have called it charge Q1, let's call this one as Q2. It has some magnitude, I guess 2 nanocoulomb. Then let's call this one Q3. It has magnitude not magnitude, it has total charge of -6 nanocoulomb. And then we have a fourth charge, Q4, again with a magnitude of 2 nanocoulomb. I say magnitude, that's like the net value of charge, but that's a positive charge. So what do you think about that first one?
Can you repeat the question one more time for question 1, please? Can you repeat the question?
Yeah, so we have this square with the charges at each of its corner, and the charges have some value. So these three charges have magnitude q, and this charge has magnitude 2 times q. Okay, so the value of charges is important here because the charge with a plus value or minus value actually decides in which direction the force will act. So in this case, all the charges have positive values, so like they are positive charges. Okay, and if you have forgotten Coulomb's law, it goes like F equals some constant times first charge, second charge divided by the distance between charges. The Q1 and Q2 here in this generic formula, it just means the two charges that you're dealing with. That has nothing to do with, let's say, this Q1 and that Q2. Okay, you can take any two charges with any name and can substitute in that formula. So we are just going to calculate the direction of force for this first one. If you have forgotten the Coulomb's law, or the force that acts between charges, it's repulsive for the charges of same sign. Positive, the force will be repulsive. If both charges are negative, the force will be repulsive. And if one charge is positive and the other is negative, the force will be attractive. Attractive means if this charge is negative, let's come to this. Since we have Q3 negative and this charge is positive, so if you want to look at the force on Q1 due to Q3, it will be towards Q3 because this Q3 is negative and it tries to pull the positive charge towards itself. So that's what it means by positive negative charge. Okay, so here all the charges are of same sign, they are positive. So if you are going to look at the force on this charge, which is at the bottom left, due to all the rest of the charges, it's all gonna be repulsive. Okay, so you can individually check that. There is a principle called superposition principle. It's very important. It says that if you have a configuration of charges, like more than one or two charges, generally more than two charges, then if you want to calculate the force on one of the charges, then you can treat the forces individually. Which means that here you have 4 different charges and you want to check the force on this charge, which is at the bottom left of the square, due to all 3 other charges. Then if, let's say you want to see which direction this charge will exert force on this charge. Then for this scenario you can ignore these 2 charges, which means you can suppose that these 2 charges, they do not exist. Okay, so if we do this, if we apply superposition principle, then we see that if we have just these 2 charges, then both are positive. So this charge will exert a force on this charge in this direction. The force will be repulsive, and so this will be the direction, right? Now if we want to check the force due to this charge on this charge, we can ignore these 2 charges. And so the force due to this charge on this charge will be in this direction, because both charges are positive, and so this charge will repel this charge. Okay, now we have this charge, so we can ignore this charge and this charge, and the force due to this charge, it will be in this direction, right? Because if you draw a straight line between them, that's the direction in which force acts, like it acts between the centers of the charges, which means the straight line. So this charge will exert a force in this direction. Okay, so here's the thing. So we have 3 different direction of forces. Okay, and forces are vector quantities. We can add vectors. Okay, so and when we deal with vector quantities, there's one important ingredient that we need to take care of, and that is to define beforehand in which direction a quantity will be positive or negative. Since vector quantities have directions, so you have to take care of directions. You have to define direction by yourself. When I say you have to define direction by yourself, that's like a freedom that we have. We as a physicist have this freedom, like which direction we choose positive and which direction we choose as negative for a given vector quantity. It doesn't, like the nature doesn't depend on which direction we choose positive and which direction we choose negative. The answer will always be consistent and right. Okay, so the general convention that you might have studied in earlier classes in books is this one. So you have this 2-dimensional plane and you define positive x-axis towards the right and positive y-axis upward direction. Okay, so we need to use this coordinate system here. So let's say that this is the origin of coordinate system, this point. Okay, so this direction is positive x and upward is positive y. And now we immediately got the signs for these forces, like in which directions they are pointed. So this blue force, it acts towards negative x-axis. Okay, so this is negative x-axis, this is a unit vector, this hat represents a unit vector. This is towards negative y-axis, and this green force has some direction. It lies somewhere between x and y-axis. You can always find that angle. Okay, so the question specifically that is in that worksheet, it asks, it gives you like a multiple choice. It asks, like, let's say this is direction A, this is B, this one is C, and this one is D. So it asks us in which direction the net force will act. So what do you think the net force will be, along A, along B, C, or D? D. Why? We see that green force is in this direction, and then we can add these 2 blue vectors, and if you add these 2 blue vectors, then we just need to take this vector and place it at the head of this blue vectors, and we see the net resultant of this 2 is along this line. And so both the blue force and the green force, they act along that direction which we have represented as D. Okay, that's what the question is. So the net force will be the sum of the magnitude of blue line and the magnitude of green line, and then you will have to find the direction, which means find the angle. Okay, we are going to do that for this problem, or the third problem, but this ends here. Okay, so same thing we are going to apply on this diagram, but in this case we also have to calculate some numeric value. The charges have some numerical values. Okay, in this case we didn't have the numerical values, we just wanted to deal with the direction. Okay, so let's apply Coulomb's law on this one. And first thing first, we need to choose our coordinates system. Okay, and since we want to see the force on this charge due to all these three charges, okay, so it's a good choice that we set our coordinate system such that this charge lies at the origin. And so my positive x-axis will be in this direction and positive y-axis will be in this direction. Okay. Once this is set, you can look for certain symmetries. So the general rule of any vector quantity, here the vector quantity is force, we are dealing with force. So general rule for any vector quantity is we resolve it into components. We see or we look for the net force which acts along different directions. So here we have two directions, x and y, and so we look for x and y components of net force. So if we first consider these two charges, superposition principle tells us that we can ignore these two, and so the force between these two charges will be repulsive. Okay, you can immediately check the direction, and since we are looking at force on Q1 due to Q2, they are positive, the force will be in this direction because of Q2. What will be the magnitude of this force? So, okay, since this force is not along x-axis or y-axis, we can resolve this force into its components. Right? So if I resolve this force into its component, one of its components will be along x-axis, in this case negative x-axis, and the other one will be along negative y-axis. So this is F12 x. F12 means the force on charge Q1 due to charge Q2, and x represents the x component. Okay, and this is equal to F12 cosine of theta. We can find theta from this diagram. And this one will be F12 y, and this will be F12 sine of theta. Okay, you see the angle between x-axis and y-axis is 90 degrees, and this line, it just bisects this axis, this first quadrant into 1/2. So this angle will be 45 degrees, and so this angle will be 45 degrees. Okay, so we find the angle theta, we found it. Now we need the magnitude of this force, F12. So F12 will be
F1x or F12x.
We can do one better, just give me a moment. Let's leave this problem here and look at the force that charge Q4 exerts on Q1.
Coulomb's law, right?
Sorry?
We're just using Coulomb's law. Like,
Yeah. So the direction will be this one,
no.
right?
So the components cancel. You just,
Yeah, exactly. So you see, we can always use symmetry, these arguments, to just get rid of some terms to save our time and calculation. So this is F14x, and this is equal to F14 cosine theta. And similarly, this is F14y, and this is equal to F14 sine of theta. And if you see, this angle again is 45 degrees.
so you could also use cosine then?
Yeah, that's what actually I wanted to do, to save our time and effort. So now you see that the x components, this one f12 cosine theta and f14 cosine theta, they are in opposite direction. And somehow if their magnitudes are also same, they'll just go away, they'll cancel each other, right? The net effect will be zero since it's a vector quantity. So if we somehow show that f12 is equal to f14, we can just get rid of x components. So if we look at the force, it depends on the magnitude of charges. The distance we know in that case is same for all charges, 5 centimeter. Okay, so f14 will be q1, q4, and f12 will be q1, q2. q1 is 17 nanocoulombs, q2 is 2, that's 34 times some constant number. q4 is 2 nanocoulombs, q1 is 17 nanocoulombs, that's again 34 times some number r and k, which are constants in this case. So we have just shown that f12 in magnitude is equal to f14, right? And so these x components goes away. So we have saved our time, right? What about these components, the y components? Okay, first thing to note is they are pointing in negative y direction, so they should be negative. Okay, and also since we have just shown that f12 is equal to f14 in magnitude, so they are same in magnitude, this one and this one, and sine theta angle is 45, so they just add up, they becomes 2 times f12 sine of angle theta. Okay, so this blue and green arrow, they give us, let me call this force the sum of sum of the two forces due to q2 and q4 on q1. I'm going to call this f prime, and this is just equal to k, some constant times. So we can pick either f12 or f14. I'm going to use f12. So this will become 2 times f12 sine of angle theta, which becomes 2 times f12, and angle is 45, and sine of 45 is 1 divided by square root 2. What about f12? So this will become square root 2. 2 divided by square root 2 is square root 2. f12, which is k times q1, 17 nanocoulombs, and q2, which is 2 nanocoulombs, divided by 5 centimeter, you convert that into meter, that becomes 5 multiplied by 10 raised power minus 2 and then square. That's it. And k has value 9 multiplied by 10 raised power 9 Newton meter squares per coulomb square. So you see we have found a numeric value for this, and the direction will be negative y-axis. So negative y-axis means whatever numerical value you find here, that's how you write it. Minus sign, this numeric value, and y-axis. So there is a way to interpret this equation. You can include this negative sign, this with this y-axis, and it immediately tells you that the force is towards negative y-axis in the downward direction, because we have defined it in the downward direction. This is this f prime is the result of the forces that Q2 and Q4 exert on Q1. We also have a third charge, Q3, and Q3 is negative, minus 6 nanocoulombs. So this Q3 will try to attract Q1 towards positive y-axis, and so since Q3 lie on the y-axis, it only has y component, it doesn't have x component. So in entire problem we don't have any force acting along x-axis, it's only along y-axis. So when you want to calculate F13, I'm going to do it here. So this will be F13, and it's along positive y-axis, so I'm going to write the unit vector beforehand, and then you have k times Q1. Q1 is 17 nanocoulombs. I'm just going to write it Q1 now. Then Q2 is minus 6 nanocoulombs, but you will use 6 nanocoulombs. Why? Why you will use 6 nanocoulombs for, Q3? Because you have already figured out the direction that it's towards positive y-axis. That's why I put positive y here. Okay, you always find the directions before even calculate the magnitude of force. So you see F13, this is the force due to Q3 on Q1, and the force, the sum of force due to other two charges is here. What will be the net force?
I think it's probably going to go up.
Yeah, probably gonna go up. So net force will be, let's call that force F. It will be the sum of these two forces. That will give you a positive answer. So F13 will give you a positive answer. So I'm gonna write it as y unit vector minus F prime y unit vector. You see, there's no negative sign which I put with y otherwise. So negative sign is here. So you subtract the magnitudes and you know that the direction will be plus y or minus y. For example, if this second term is greater than first term, you will eventually get a negative answer which tells you that the net force is in the downward direction. And if your first term, like this answer, whatever we get here, if it's greater than the second one, you get a positive answer, which means this charge will move in the upward direction. I did some calculation, I had a numerical answer. It turns out that this charge actually moves upward. The force is towards positive x-axis. I didn't calculate the numeric values here, they don't matter. The thing to understand is like how you follow a problem. You can just substitute these values which are given in the problem and find a numeric answer. Questions? You good? Okay, next one is interesting. I'm gonna solve it here. So the third one, we have a charge in the presence of an electric field. So we have Q3. So here's a situation. So we have a charge hanging by a thread from a ceiling. So let's say this is the charge. Okay, it's charge Q. It's plus Q. It's given. And then you apply some electric field. Okay, I chose the direction as this direction of electric field. And since it's electric field, it exerts a force on this charge and the charge ends up in this direction. Okay, good. And the charge is in equilibrium in this direction. Okay, which means that it just stays here under this electric field. Charge has some mass, it's given. It has some mass and thread has some length. Let's actually look at the values. And so you're supposed to calculate the value of this charge in this situation. And please remind me, I need your attendance too. Okay, worksheet this. So the charge has mass 8.50 grams and the thread has length 25 centimeter. And the electric field has value 1750 Newton per Coulomb. That's it. We need to find the charge. So under the action of this electric field, the system is in equilibrium. The charge is at this position. So how we are going to find this charge?
You take Newton's second law with gravity.
Yeah.
Just find the charge that way.
Great. I'm glad. In fact, this Newton's law is the single most important thing in all of classical physics and even the modern physics that you are entering now. It's just everywhere. So you see, when I say that the system is in equilibrium at this point, it immediately tells us that there is no net force on this charge. You see, we are moving towards Newton's second law. When it says no net force, you see Newton's second law is sum of all the forces on any object, it's equals to mass time acceleration. Also, this is a vector equation, which means we can write this equation as this one. One component along x-axis and the other one along y-axis for two-dimensional cases. Okay. And now, if the system is in equilibrium, how do you define equilibrium? Either the object is at rest or it's moving with constant velocity. In both of these cases, acceleration is the rate of change of velocity. So if the velocity is 0, acceleration will be 0. If velocity is constant, the rate of change of the constant will be 0. Okay, and so in both of these cases the acceleration is 0, and every time when the system is in equilibrium you define this condition that the sum of all the forces should be 0 from Newton's second law. And since we have sum of all the forces on the object equals 0, which means we need to figure out all the forces. Once we do that, we can write the forces, all the forces along x-axis and all the forces acting along y-axis, and that's it. That is like the most important step in all of classical physics in solving problem. In all of classical dynamics, we have two parts, kinematics and dynamics. Dynamics deals with forces, like how the objects evolve in time. Okay, that's it. So first thing first, since the object has some mass, so it should have some weight, and this should be equal to mass times acceleration due to gravity. Then we see that the electric field, and first thing I forgot, what is the most important thing? We need to define our coordinate system, and a prudent choice would be that we put this charge at the origin of coordinate system, positive x, positive y, right? Now we are good. Electric field then is acting purely along positive x-axis. Okay. What else is there? Any other force?
Can we count the tension in the string?
Yeah, of course. So we have tension in this direction. Also, in the problem statement, you are given that this angle is 60 degree. Okay, then this angle is 30 degree. And if we can immediately find the components of tension, since tension is neither along x-axis nor y-axis, it makes some angle, we need its components. We see that this component will be t sine 30, and this component will be t cosine 30. You got it? This angle is theta. In this triangle, the perpendicular side is this one, so this gives us sine theta, and this is the base of the triangle, this gives us cosine theta. And now we have all the forces which are acting along x-axis and along y-axis. I'm going to use this expression. So summation fx equals 0. This gives us E is along positive x-axis, so it is E, and t sine theta is along negative x-axis. So negative x-axis, this negative sign. So t sine 30 equals 0. And similarly, summation fy equals 0 gives us t cosine theta is along positive y-axis, so t cosine 30 is positive and weight is negative. Okay, equals 0. Where is Q, the thing that we actually want to find? It's inside electric field. The expression for electric field is Q times F, and F is that Coulomb's force. Okay. So we don't know T. So we have two equations, both contains T, so we can calculate T from this expression. Let's say T will be mg divided by cos 30 degrees. Okay. So we can find tension from this second equation, and we can substitute this tension into the first expression. First expression is E equals T sine 30, and if we substitute for T, this will become mg tan 30 degree, right? Because T is mg divided by cosine 30, sine 30 divided by cosine 30 will be tan 30. And E, we know that, this is not E, this should be force, electric force, since we are writing this Newton's second law for forces, not for electric field. Okay, so F, this is actually F, and so F is Q times E, and we need Q. So we can immediately see that this will be mg tan 30 degree divided by electric field, and now you have mass of the charge, you know the value of acceleration due to gravity, tan 30, we know that. Electric field, it's 1750 newtons per coulomb. So you can find a numerical value for this charge. Make sure that units turns out to be coulombs. Questions?
Well, F equals T sine 30, and then the next line, what does it say? Q, is that Q?
No, this. So we had this direction is electric field. Thank you for pointing this out. I mean, I caught it, but still. But the relation between force and electric field is F equals Q times E. Yeah, and these expressions, we are looking at forces acting along x-axis. Okay, so we have electric force acting along x-axis, and that's why we use Fe minus T sine 30. So we have electric force Fe acting along positive x-axis. Electric force, since it has the same direction as the electric field is along positive x-axis, which means the associated force is also along positive x-axis. But the relation between electric force and electric field is this one, F equals Q times E. So we have electric force along positive x-axis minus T sine 30. And yeah, here it's correct. We got the mistake. Okay. So we substitute Q times E in place of electric force, and then we find Q.
Okay.
Okay.